So our speaker today is Dr. Ball, our own Dr. Ball. And he's going to be telling us about the kilonovas, not to be confused with the killer novas from Star Trek. Okay? I guess it's the kilonova. After Dr. Ball presents, there'll be some time for questions. And if you want to continue your questions, we'll be having a lunch, I assume, yes, at the Joyce Room in the Corner Cafe. So if you want to join Dr. Ball and some other people to talk more informally about these things, please join us in the Joyce Room in the Corner Cafe. Let's give Dr. Ball a warm welcome.
Thank you for coming out to the first science seminar of the fall semester. And thank you, Dr. DeVoe, for organizing the science seminar. I want to start off by praying for you. Let's have a word. Father God, I just thank you for these precious young people that are here studying here at LeTourneau University. And I just pray that you'll help them to get a good start on this semester. Lord, help them to focus on the things that they need to focus on and put aside the distractions, God, and may they not forget you, Lord, during this entire semester and this entire school year. May they be reminded again and again that you are with them, Lord, and your grace is abundant even today, Lord. We pray for your blessing upon our time together here and now. In Jesus' name we pray. Amen. Amen. All righty. I was asked to come and give a talk on something called a kilonova at a meeting up in Canada at Trinity Western University back in May. That's why the date, May 14th, is up there. And so I am not a professional astronomer, so you find out why was I asked to give the talk. Well, I think they had a hard time finding somebody else. I think that was the reason. But anyway, I agreed to do it. And because I was so excited about the discovery of something called a kilonova. And I'm going to try to describe what a kilonova is for you during today's seminar and why it is such an exciting new development in all of astronomy. It really represents a new era in astronomy, if you will. And I better not shine this in your eyes. This is a green laser pointer and it's bright. So I'm going to use it as my pointer today. My astronomy students love it when I go outside and use the green laser pointer to show them things in the sky. So I'm going to use it today with you as well. Astronomy really took a major shift back in 2015 when the so-called LIGO interferometers came online and started working, because it represented a way to discover something other than electromagnetic waves coming to us from outside the Earth. Everything that we detect from outside our Earth seems to be coming, before then, only in the form of electromagnetic waves, light, or other wavelengths of electromagnetic radiation, radio waves, and X-rays, and gamma rays, and UV, and ultraviolet, and infrared. Okay, all of these wavelengths of the electromagnetic spectrum were the sources of information we have from distant astronomical objects, extraterrestrial objects, if you will. We had to send several of these telescopes out into space because most of those wavelengths won't make it through our atmosphere. Only the visible and the radio and some of the microwave makes it through the atmosphere. But those other forms of electromagnetic radiation do not. And so we had to launch these telescopes up into space. And so the Hubble telescope and then other telescopes that could see, you'll see today a gamma ray telescope that was launched up into space called the Fermi Gamma ray telescope is being used today as well. That really represented a huge expansion to astronomy, to be able to see all of those different wavelengths once we began to launch telescopes up into space. But that still only represented electromagnetic waves. Starting in 2015, the LIGO project finally got underway. The LIGO, Long Interferometric Gravitational Wave Observatory. That is what LIGO stands for. Two of them came online. One of them in Hanford, Washington, way up in Washington State, and one of them close by here in Livingston, Louisiana, a couple kilometers long. An interferometer, I'm not going to take time to describe an interferometer to you today, only to say that it's a, you split the light into two different beams, if you will, and they have mirrors at the end where they come back, and how they interfere with each other gives you an indication of one path length compared to the other. And so these were set so that they would null each other out right in the center. And if there was no distortion of the links of either arm, then they should null each other out to 0 amplitude, right, when they come back together. These were designed to be extremely sensitive to stretches of space. Very tiny stretches of space, or compressions of space, where space itself would be stretched or compressed ever so slightly in one dimension as compared to the other. Then the two beams would not null each other out, but would give you a non-zero signal in that sense. But you might, as you might imagine, noise would be a huge problem. Any kind of earth shaking mechanism would cause an enormous signal in such a detector. So they had to find ways, very ingenious ways, of getting rid of all of that noise and sort of isolating these interferometers from noise. And even at that, it became an enormous challenge to overcome any and all possible sources of noise. So I'm not going to go into that, but just to say that this was an enormous accomplishment, so that you could begin to see the changes in links on the order of 1/1000th the width of a proton. So that you could begin to see changes in links on the order of 1/1000th the diameter of a proton. That's 10 to the minus 18 meters. A proton is about a femtometer, 10 to the minus 15 meters across. This had to be designed to see changes in length of 1/1000th of that size, the size of the proton. So this was an enormous accomplishment. And when these came online, we immediately began to see some signals. And I'm going to show you that in just a moment. The Virgo Observatory over in Pisa, Italy, did not come online until just last year. So this one came online in 2015. They ramped it up to the advanced stage that it was in when the discoveries were made that I'm going to show you. And then Virgo came online in 2017. Taking together all of these different gravitational wave observatories, you could then begin to not only see a signal, a gravitational wave passing through your detector, you could also begin to locate what direction it came from. Okay, so that was the idea of why they had to build 3 of these observatories around the world, so that they could measure the time of the signal and locate exactly where the signal was coming from in space. This represented a huge, huge advance in astronomy, as I'm going to show you in just a moment. But what would cause sources of gravitational waves to be emitted? Well, anytime you rapidly accelerate a mass, it creates a gravitational wave. So I just created a gravitational wave. But the strength of the signal of the gravitational wave I just created would be far too small for us to detect in this kind of detector. So it would require a very massive object being accelerated rapidly, very rapidly, to create a gravitational wave that we could begin to detect in an observatory like this. And so one source of gravitational waves would be a binary system of 2 pulsars, or 2 neutron stars, in orbit, in close orbit about each other. 2 neutron stars. Now, what's a neutron star? Neutron star is what is the final leftover stage of a dying heavy mass star. A massive star, when it dies, it undergoes a very dramatic ending when it goes supernova, and the outer shell gets blown off, but the core gets compacted. How far does it get compacted? As far as gravity will allow it to compact it. What's to prevent gravity from just completely crushing it to a point? Virtually nothing, but there is something for a neutron star, and that is the neutron degeneracy pressure. You cannot seem to pack neutrons into the same space. They're what's called fermions. They don't like to occupy the same point in space, and so they will repel each other. And so that's the only force that we know of at that stage that's able to prevent gravity from completely crushing the core into a point. And so, but you have a very, very dense object when you have a neutron star. You have something that is several times the mass of our sun compacted into 10 to 20 kilometers across. That's the density of a neutron star. It has the same density as the atomic nucleus. The same density as the atomic nucleus, but it's 10 to 20 kilometers across. And the escape velocity is approaching the speed of light. The escape velocity, trying to get anything to escape from the surface of a neutron star, it has to be moving nearly the speed of light. So you're approaching something called a black hole. You're approaching something called a black hole when you have something that dense and massive. So neutron stars were discovered actually by accident back in 1967 when a female astronomer, Jocelyn Bell, she detected a radio signal coming to us that made regular blips, blip, 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 blip. And at first we thought, of course, it was extraterrestrial intelligence trying to contact us. They labeled it Project LGM and classified it secret. Little green men. But other astronomers, when they finally got wind of it, said, oh, that's not extraterrestrial intelligence. That is a rapidly rotating neutron star. Because when a neutron star is produced by a supernova process, any initial spinning action that the star might have had is spun up greatly, is greatly spun up. Conservation of total angular momentum, if you've had physics 1. So that star, when it's crushed, any spinning action, that angular momentum is conserved, and that whole thing is really spinning several times a second, about a second. In fact, it could be spinning up to 100 times or more per second about its axis. Something 10 to 20 kilometers across, spinning 100 times per second. It's just hard for us to fathom. So the outside edge of the neutron star is approaching the speed of light. Anyway, that is a rapidly rotating neutron star, and we call it a pulsar because we can detect the pulses given off when light is shot out through the magnetic poles, kind of like our auroras here on Earth, only much, much greater effect than our auroras here on Earth. You have radiation that's coming out of the magnetic poles of a neutron star, and every time that magnetic pole kind of swings and points at us, it sends us a signal, and we receive blip, 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 blip. And so that was what astronomers knew that these pulsars were, rapidly rotating neutron stars. Now, if there were rapidly rotating neutron stars, could there be neutron stars that have a binary partner that they're orbiting about? Well, sure, most stars don't come as single stars. Most stars actually come in multiple star systems, binary systems, or more. Like the next nearest star system to us is the Centauri system. It has Alpha, Beta, and Proxima Centauri. It has 3 stars orbiting around each other. That's the nearest star system to us, and it has 3 stars. So most star systems are actually binaries or more, but usually one star is so much brighter than the others, you can't even see the others. And so we don't easily see binary systems, by the way. They're not easy to see. Some are. One of the Dipper arms, the middle of the arm of the Big Dipper is a binary system, and it's a visual binary. You can actually see both stars in there when you magnify it in the telescope. But anyway, most stars come in binary systems. So it made sense that if neutron stars exist as pulsars, then you might have binary pulsar systems. And so even way back in the late 1960s, it was predicted that a binary pulsar system would then be an excellent place to test Einstein's theory of general relativity. Why? Because Einstein's theory of general relativity, it governs the motion of all matter, and it's known that Isaac Newton's theory of gravity is only an approximation of Einstein's theory of general relativity. Isaac Newton, we use his equations to map out where all of the planets are going to be centuries from now, and it's very, very accurate, right? We use Newtonian gravity, but it's only an approximation because it treats time as if time is the same for everyone, everywhere, which Einstein's theory of relativity does not. Time depends upon your frame of reference, and space-time is measured in one frame is different from space-time is measured in another frame. And so the full theory of general relativity involves a theory that connects matter, space, and time together in such a way that is a little bit, makes it a little bit more complicated for a system than Newtonian gravity would. In fact, one major difference between the two theories is that according to Newtonian gravity, these binary pulsars, in the absence of anything else around them, should always orbit each other with the same period forever. That would be one prediction of Isaac Newton's gravity, was they should never have any orbital decay at all. But one prediction made by the theory of general relativity that differs from that is that the orbit of each binary partner should decay through the emission of gravitational waves. Any mass that's accelerated emits gravitational waves, and so gravitational waves are constantly being emitted by any accelerated mass. And so these binary partners are constantly being accelerated around each other, so they're constantly emitting gravitational waves. But where does that energy come from, and where does it go? Well, it goes into the form of gravitational waves that spread outward, but it saps the energy of that system. So the orbits begin to decay. It begins to decay the orbits. And over time, this is the cumulative shift of the para-astron time. The orbital period begins to get smaller and smaller and smaller. This curve is the prediction of general relativity for a binary system that was located shortly after pulsars were discovered. And these two guys, Taylor and Halsey, received a Nobel Prize for showing that the observation of the period of these guys orbiting about each other exactly matches the prediction of general relativity. So here is a very, very accurate test of general relativity. And it's given us a lot of confidence that Einstein's theory of general relativity is actually very precise and accurate, and it models a system like this very well. So indirectly, we already knew gravitational waves should be emitted, and they had to be, but this is only an indirect observation of gravitational waves. What would be nice would be a direct observation, a detection of whether a gravitational wave actually passed right through us. How would we see that? So that was the question. If you have, say, two binary black holes, even more massive and more dense than neutron stars, orbiting about each other, then that would only increase the strength of the gravitational waves being emitted. So the frequency would increase, and the strength, the amplitude would increase as you, we've been talking about frequency and amplitude in the physics class here. Anyway, the amplitude and the frequency both increase greatly in a system like this because gravity's all the stronger. And here is a simulation. This is not an actual picture taken of two black holes. You can't see a black hole, first of all. Light cannot escape from a black hole. The escape velocity becomes greater than that of speed of light, so no light escapes from a black hole. But this is still just a simulation of what space-time would look like to an observer watching from a very unsafe distance two black holes orbiting about each other. And I'm not going to show you what this looks like in real time because when they get this close, they're orbiting around each other up to 300 times a second, right before those event horizons merge together. Right before the event horizons merge together, they're orbiting 300 times a second. So I can't show you this in real time anyway. It would just go blip and be over. But gravitational waves are being emitted before they merge together. There are gravitational waves that are spreading outward from this system. This is a representation. This is not what you would see in real space looking at the light like this one, but this one just represents in a two-dimensional sense, a two-dimensional space fabric. The gravitational waves are spreading outward from those two black holes as they're approaching merger. The merger happens when the two event horizons of the black hole touch, and it becomes one black hole, and the masses combine together. All righty, what did we see way back in 2015? Ooh, it's hard to imagine. That was just 3 years ago now. And then that next spring is when they announced the discovery, and Dr. Hamilton and I gave a science seminar, an evening seminar on what's the significance of the discovery of gravitational waves. And it was so exciting. And so we talked about it then. But, you know, it was exciting, but there was one thing missing, and that was any kind of electromagnetic waves coming from that event. And so this event, the black hole merger that was discovered by LIGO, the LIGO interferometers, on September 14, 2015, this is the signal that was seen in the Hanford, Washington LIGO interferometer. This is the signal that was seen in the Livingston, Louisiana interferometer. This is the theoretical curve that should have been received if it were a merging binary black hole system. A merging binary black hole system should give a signal like this, or this. And you can see that it matches very accurately what we actually observed. Of course, there was some residual noise, that you always deal with residual noise, but this was a signal above the noise. And this represents a strain. That is the change in length divided by the length of those interferometer arms. The interferometer arms, remember, they're a couple of kilometers across, a couple of kilometers, 10 to the third power meters. And we're looking for something that's 10 to the minus 18 meters of stretching. So 10 to the minus 18 and divided by 10 to the third gives you 10 to the minus 21. That is the strain that was being observed in the LIGO interferometers. And for them to be able to see that stretching, as the gravitational wave passed through it, it stretched in one dimension, the space compared to the other arm, just enough so that the signal could be seen in the interferometer. The frequency increases as the frequency is getting stronger, higher and higher and higher, until finally you see 300 times per second before the merger takes place. So this was discovery of gravitational waves, direct discovery of gravitational waves made in 2015 by the LIGO interferometers. And of course, those guys received a Nobel Prize as well. But one thing's still missing. What's missing is we couldn't see any electromagnetic radiation coming from this system, right? Only gravitational waves, because it's black holes. A kilonova would be more interesting because binary neutron stars, they emit light, electromagnetic waves, and they should be emitting gravitational waves while they approach merger. So that would be even more interesting. So finally, Virgo came online in 2017, and right after Virgo came online, there was a signal detected in all three sites, the Hanford site, Washington, Livingston, Louisiana, and Virgo in Pisa, Italy. Of course, not much of a signal there. I'll talk about that more in a moment. But the signals that were seen passing through these gravitational wave observatories could be seen as signals above the background noise in all three of them. This one's kind of a stretch, but anyway, Livingston, Louisiana saw the strongest signal to noise. The strongest signal to noise ratio of about over 14 times the signal to noise. So this one was the strongest signal that was seen. This was a very interesting looking signal. Why was it different from the others? There were 4 others that occurred before it, and they were all binary black hole systems that merged together, where the total mass was many times the mass of our sun. In fact, the very first one that was discovered, I think, was 65 times the mass of our sun, the combined mass of both black holes. So neutron stars only go up to about 2 solar masses before they begin to collapse into a black hole. That number's a little bit it's poorly known what that exact number is, but it's about 2 solar masses. If you get more than 2 solar masses, roughly, a neutron star will be collapsed into a black hole. So you had to get a less massive system to get a binary pulsar. A binary pulsar system would not be as massive. Furthermore, it would not radiate, the frequency wouldn't jump up to 300 hertz that quickly. It would be a slow buildup over time, and it would be a weaker signal. It would be a slower buildup towards merger and a weaker signal if it were truly a binary pulsar system. But because it would be a weaker signal, these detectors were not able to see something a billion light years away. If it were a binary pulsar system, the signal would be too weak by the time it got to us. So it would have to be within about 100 million light years, which is, astronomically speaking, much closer. 100 million light years is not that far when you're talking about a billion light years away. And that's where all of the mergers of black holes that we saw, the 4 times that we saw mergers of black holes prior to this, they were all about a billion light years away or more. And but we were able to see the signals because the gravitational waves emitted by those systems were so strong that even by the time they reached us, we could still see the signal. The binary pulsar system would have to be within about 100 million light years away for us to see the strength of the signal as it approached merger. And sure enough, this one was a slow buildup. We saw it over 100 seconds. We could begin to see the buildup of this one. I don't show all the 100 seconds there. I only show the last half second or so. But the buildup of the signals could be seen, particularly in the Livingston site, from over about 100 seconds until the merger was reached. So that was a good indicator that it was a lighter system that was approaching merger. And it didn't reach 300 hertz. It didn't reach that frequency. So this was an indicator that it was probably a lighter mass system that was approaching merger. Now, we had to see something else if it was truly a binary system of pulsars or neutron stars. We had to see electromagnetic waves being emitted by them as well. And that's where the story gets more interesting. The Fermi Gamma Space Telescope is looking at it's actually looking at all regions of the sky at once. But it's able to localize where a signal is coming from just barely. And it observed the signal 1.7 seconds later than the gravitational wave observatories observed them. And I'll talk about that delay in just a moment. So here's the gravitational waves. And then 1.7 seconds later, blip, a gamma ray burst is detected by the Fermi Gamma Space Telescope. And furthermore, they try to localize where those signals were coming from in the sky. Now, with the 3 gravitational wave observatories, we're able to localize a very small strip of the sky where it had to come from. And so, with Virgo included, there was a region of the sky where that source had to come from. Fermi, by itself, was only able to localize this region of the sky, but still, it overlapped. So probably the same source. Probably the same source emitted both. So, now it's getting interesting. We are now what's called the era of multi-messenger astronomy. The era of multi-messenger astronomy. Here comes the gravitational wave. Look, the LIGO observatories feel it, and the Gamma Space Telescope sees it. Okay, that was so good, I'm going to play it again. Here it comes, gravitational wave. Ooh, did you feel it? No, I didn't feel it. Oh, I saw it. So we are now in the era of multi-messenger astronomy, where we're able to see both gravitational waves and electromagnetic waves coming from the same source, if we're able to be fortunate enough to turn our telescopes toward that
in time. Well, how about visible light? Now, I'll get to that in a moment. We saw it in gamma ray and we saw it in gravitational waves, but boy, it'd sure be better if we could localize it and see it in visible light, right? Well, oh, one more time. Sorry. Anyway, I like this little cartoon because it gives you the gist of what multi-messenger astronomy is. There was a frantic search amongst the telescopes in the southern hemisphere. Why? Because this was observed in the southern hemisphere. So the telescopes in the northern hemisphere were of no use to us, and fine, we couldn't begin to see it. So, but all of the telescopes in the southern hemisphere began a frantic search for where this was coming from. And while you can localize it to a certain strip of the sky, there's a lot, as you're going to see in just a moment, there was a lot in that strip of the sky to try to visually, to actually find exactly what the galaxy that it was originating from. In fact, let me give you a sense of that. It was found by the Swope telescope in Chile a little over 10 hours after the gravitational wave signals and the gamma ray signals were observed. In the constellation Hydra, on the outskirts of this galaxy NGC 4993, but I've got to show you how hard this hunt was. I want you to get an impression of the, oh, I didn't want it to come up in, let me, oh, there it is. I want you to hear this. This is how hard the hunt was. You're having to search all of these possible sources. And they found it. In this galaxy right here. 130 million light years away. Started off as a blue signal, and then it reddened out. Very strong blue signal, and then it reddened out over time. That was the electromagnetic rays that we observed coming from this particular source. So you see two images taken by the Swope and Magellan telescopes. This one on August 17th, right here, there's the blue signal on the outskirts of galaxy NGC 4993. We don't even have a name for this galaxy. It's so far away and so dim that it's just cataloged with this number. A very strong blue source brightens to nearly the brightness of the galaxy and then begins to dim out and redden. Begins to redden. That was very crucial information to help us to figure out what in the world is going on with this type of event. Why do we call it a kilonova? Because there's two kinds of novas you might have heard of if you've been into astronomy. One's a nova and one's a supernova. Well, a supernova is a million times as bright, typically, as a nova. A nova is just a brightening of a star for a short time. It becomes brighter in the sky, but a supernova becomes a million times brighter over the course of a few days. But those were two radical extremes of brightening of star events. This one was only about 1,000 times brighter than a nova, so we called it kilonova. And this was the prediction that a merging binary black hole, neutron star system, would be about that bright. So these were the ground-based observatories, and you can see that in this cute little image, which observatories were responsible for detecting the brightness of that event over the course of several days. It got brighter over the course of the first day, and these two observatories here in Chile and Australia, and other observatories, Africa, back to South America, back to Australia, these observatories were measuring the brightness curve of this event and how it changed from blue and reddened out over time, over several days, okay? So now you've got a wealth of information, and this wealth of information is allowing us to reconstruct what happened. Now, to the best of our ability, what actually happened. To the best of our ability, we model what the kilonova event must have looked like, okay? I'm going to try to describe this to you really quickly. It'll have to be quick. Here's two orbiting neutron stars approaching a merger. Two orbiting neutron stars approaching a merger. In other words, they're very close. If they're only 10 to 20 kilometers across, then you can see that they're approaching within 100 kilometers of each other or so as they're approaching a merger. Their orbits are decaying through the emission of gravitational waves. You'll see you can't see gravitational waves, but it shows gravitational waves being emitted by these neutron stars as their orbits deteriorate. Finally, it approaches a merger. And when it merges, an enormous explosion takes place. And those neutrons that were packed into each neutron star begin to be expelled from the surface of each neutron star. They mix, and they're able to undergo fusion up to heavier elements in a very short time in this dense, rich, thick soup of neutrons. You're able in a very, very short time to build up heavy elements. Now, one question that has really fascinated people for a long time is, where do the elements originate? Where do the elements originate? Well, we've known now for several decades that the Big Bang origin of the universe could only produce essentially hydrogen and helium. The universe would be all hydrogen and helium if it were just up to the Big Bang. Because a simple model of the Big Bang shows that the universe should be 75% hydrogen by mass and 25% helium by mass, and very little of anything else. But as you and I know, we're not made up of hydrogen and helium. We're made up of carbon and oxygen, magnesium, and all these other wonderful heavier elements, right? Where do they come from? Well, for the longest time, we assumed that they were all built up inside of the fusion processes and the cores of heavy mass stars. And that when that star died a violent supernova death, it expelled a lot of those heavy elements into outward into space. But how do you build up heavier than iron? Because you've got a problem here. Iron is the most compact atomic nucleus there is. And when the star goes supernova, it's because a buildup of iron takes place in the core, the central core of that star. And when you fuse iron, you don't get a release of energy. It's an endothermic reaction. It cools off. And so how do you get elements heavier than iron? Well, the speculations were that maybe in the supernova process it was so hot that even in the expanding cloud of matter, temperatures high enough were reached to force the fusion to continue up to heavier elements, even as the supernova expanded. But the models didn't really give much encouragement to that idea for the longest time. And the biggest problem with the models was we knew that over 90% of the energy being emitted by a supernova explosion is in the form of neutrinos. And neutrinos just pass right through matter. They don't really interact with matter very well at all. And so all these models of a supernova were really failing to show how do you get the heavier elements beyond iron. So where do gold, silver, platinum, uranium, where do they come from? Why do we see all these heavy elements lying around? Where were they built up? If they weren't built up in the supernova explosions of heavy, dying, high-mass stars, then how do we get them? Well, we've got a new idea now of where these heavy elements were predominantly produced. Kilonovas. Kilonovas. Why would this be such a good place to build up the very heavy elements? First of all, it's very neutron rich. Neutron stars, high density of neutrons. So you've got a lot of free neutrons running around. And extreme temperatures, and the density is high enough of these free neutrons to actually undergo what's called the R process of nucleosynthesis. Let me describe what the R process is. I only have a few minutes, so I better get through this. Let's see if you can learn some nuclear physics in a few minutes here. This is the chart of the nuclides. The chart of the nuclides are number of neutrons along this axis, number of protons along this axis. There's the so-called curve of stability. And the curve of stability are those isotopes that are stable. They're stable isotopes. And you have roughly equal numbers of neutrons and protons for light elements, right? But once you begin to get to heavier elements, the repulsion between the protons gets so significant that you actually get a preference of neutrons over protons, and the curve of stability takes off in this direction. So more neutrons than protons. So those elements that are in black are the so-called stable isotopes. And the heaviest stable isotope we know about are up here in this region, although there's been speculations of islands of stability higher up. But anyway, these are the known stable isotopes in the chart of the nuclides. Once you go off away from either direction, above or below the curve of stability of the chart of nuclides, you have radioactive elements. Radioactive elements, and they won't last. They'll eventually decay. And beta decay will always take you back to the curve of stability. Beta decays take you back to the curve of stability. The rapid process of neutron nucleosynthesis is the buildup of heavy elements through rapid capture of the neutrons, so rapid that it's more rapid than the beta decays can take you back to the curve of stability. That's what the R process of nucleosynthesis represents. So you can go way out here, away from the curve of stability for a short time, and you have certain drip lines of magic numbers like 82, kind of like the atomic periodic table of elements has magic numbers where you have full shells. The nucleus can have magic numbers as well. So here's the drip line of 82, here's the drip line of 126. But anyway, before you can build up the, before beta decay can take you back to the curve of stability, you're out here in this region with the R process. R process takes you out here into this neutron-rich region of, and then of course beta decay will eventually bring you back to the stable isotopes. Okay, so we know that the R process of nucleosynthesis gives you a certain distribution of isotopes that is different from the slow process, and so this was known for some time. But where would you find a place in the whole universe where the R process would be favorable? Right there, killing them. So, I tried to teach you a little bit of nuclear physics, and now let's look at the origin of the elements. This is our new periodic table of the elements containing information that's normally not on the periodic table of the elements. This is information you normally don't see on just any old periodic table of elements. This shows you where we believe those elements were produced. In the Big Bang, mostly hydrogen and helium. So that was where hydrogen and helium come from the original hot expansion of the universe itself. But exploding massive stars do account for much of the lighter elements, all the way up to iron. But it's hard for us to produce elements much heavier than iron with this process, right? Because of the difficulty of producing the more and more massive isotopes. And even exploding white dwarfs are responsible for some of these elements as well. But now there's a new one on this chart. Right here, merging neutron stars, kilonovas. That we believe that the kilonovas that take place produce these elements much heavier than iron. And you're talking about these, what's your favorite element? Is it osmium, iridium, platinum, or is it gold? Or is it mercury, or is it lead, or is it bismuth, or is it up to uranium? Well, all of those are probably produced most commonly through the process of kilonovas. Kilonova events is where we believe those are manufactured. Couldn't come from merging black holes because the matter doesn't escape. The merging black hole is still in there. But the matter can escape
from a kilonova process, because gravity's not yet reached the speed, the escape velocity is below the speed of light, so matter can't escape from emerging binary neutron star system. And so this is where we believe many of the heaviest elements, the heavy metals, are produced in the universe. There's one more thing, if I got just a minute. We learned something else from this study. Because we know what the strength of the gravitational wave should be coming to us from 130 million light years away, we can measure that strength of the gravitational waves. We know how strong it should be from general relativity. And so you could say, that's a distance indicator right there. That's a good way to get a distance indicator is from the strength of the gravitational wave signal. And then if you combine it together with the so-called Doppler shift, or the redshift of that entire galaxy, and how fast it's moving away from us, you can get a measure of the so-called Hubble expansion rate of the universe, how fast the universe is expanding. Now, there's been difficulties trying to measure the Hubble expansion rate from two completely different sources. One of them has been the cosmic microwave background radiation. The cosmic microwave background radiation has given us a best fit of the Hubble expansion rate of slightly below 70 kilometers per second per megaparsec. And the data from type 1a supernovae that gives us a distance indicator out to the very limits of the universe, that's given us a slightly different expansion rate, slightly higher than 70 kilometers per second per megaparsec. In fact, they don't agree too well. They're a couple of standard deviations away from each other. I don't know if they're statistically in conflict with each other. Maybe statistically they're just on the edge of being compatible with each other. And so we thought we would use this one, the gravitational waves coming from emerging binary neutron stars, to give us an indicator of the Hubble expansion rate of the universe. The trouble is, it's so close to us. It's only 130 million light years away. I know that sounds like a long distance, but that's not very far. That's not far enough to null out the effects of individual motions, random motions, about their own supercluster of galaxies. That can have a strong effect upon the motion of the galaxy. And that sort of gets nulled out or dwarfed compared to the expansion rate of the universe as you get out to 1 billion light years or more. But within 130 million light years, you still have to deal with the randomized motion of the galaxy. And that's why this thing is so uncertain. But it's interesting that the average value coming from this gravitational wave signal gives us right in the middle between them. So who knows? Maybe they are compatible. But anyway, if we continue to measure, why are the gravitational wave detectors not working right now? Because they're trying to ramp up the sensitivity of these detectors so that we can see kilonova events coming from as far away as not just 130 million light years away, but 1 billion light years away. That's why they're being to increase the sensitivity of those gravitational wave detectors right now. So who knows what's in store for the next generation? In other words, the conclusion here is that kilonovas represent a new era in astronomy.
We have time for 1 or 2 questions for Dr. Ball. Yes, sir.
How fast do gravitational waves travel?
They move at the speed of light.
Okay.
And this was a good test. We found that it's completely compatible because it arrived 1.7 seconds before the gamma rays did. They both had to be moving at us at the speed of light. Yes. Yes.
So why I was wondering, because you said that that there's like a butter zone between like the star turning into a black hole and like a pulsar. So
Right.
why don't two pulsars merging? Why doesn't that create a black hole?
It may. What may be the leftover remnant of those two merged pulsars may be a black hole now. We don't know. That's a good question. It's probably right on the border. Do you know whether they think it's a black hole now or still a massive neutron star? It's right on that range of uncertainty, but it may well be a black hole now. That's a good question. Yeah, a couple of other quick questions. I don't know who's first. Jonathan?
Well, I was thinking, so you're saying they're speculating that a pulsar could be where some of the heavier elements come from. My question would then be, if it was a black hole, why isn't there not a black hole like somewhere in our galaxy right
They're
now?
all. I don't want to scare you, but there's plenty of black holes in our own galaxy, and there's a supermassive one at the center of our galaxy. But I wouldn't be too afraid.
Was the distance of this kilonova event determined by analyzing not only the light, but also the strength of the
Good
gravitational
question.
signal?
No, it was independently determined by the visible light that we saw coming from the galaxy, and using the Doppler shift of how fast that galaxy is moving away from us, and applying the known Hubble rate to determine the distance. And so that's how we got the distance of 130 million light
What
years.
about that
But then you can use the
1.7
gravitational wave strength itself to get an independent measure of that distance.
What about that 1.7-second shift?
Right, there should have been a delay if they were both moving at us at the speed of light. And the reason why there should have been a delay, the gamma rays were not emitted when the merger took place. They were emitted after the merger took place, and the matter began to expand away from the neutron stars and begin to undergo lots of nuclear reactions. That's what gave off the gamma rays, all those nuclear reactions that took place in that expanding soup after the merger took place. And so that was the delay.
Would that time difference be the same at different distances then?
That should be the same delay. I think no matter, if they're both moving to us at the speed of light, that should be the same delay regardless of the distance.
Okay, we can have more questions over lunch. I want to remind you that next week, we at the same time, oh, don't go yet. Let's get that down. I gotta hold you back. Next week, we'll be at the same time, and the topic will be chemistry in the U.S. Space Force, reactions with oxygen atoms, space vehicle effluents. So that'll be next week, Thursday, 11 a.m. You're very welcome. Let's thank Dr. Ball one more time.
Don't log out.
Doesn't work, did the
Uh-oh, we lost it. They should have gone around.
Did the sheets go around already, or where?
They should have.
Okay, they're hiding.
But they're floating around somewhere, yeah.
Dr.